Hello, we have a classic pendulum, except this time it's on Mars. Wow, shocking. Alright, context, yeah, who cares? It's got a mass of 2.3 kgs. Excellent. And it is on a string of some sort of 1.83 meters. I'm just going to label on our diagram 2.3 kgs. So we do know the mass and we do know the length. And we're told the gravitational field strength, G, is 3.72. Right, so if this was a pendulum on Earth, we'd take it as 9.81. Here on Mars, it's 3.72. Show that the time period of the pendulum is 4.41 seconds. Great, so on your formula sheet, you should look near the bottom. I think it's on the bottom. For time period, T, and this is a classic simple harmonic motion question. In this case, it's a pendulum. So you're looking for the time period of a pendulum equation, which you probably would have done experiments on, which is equal to 2 pi times length divided by g square rooted. Right, the other equation there, you'll notice a k and an x. That is the time period of a spring and mass system. Okay, so we found the formula we're using. Time period t, we know pi, we know the length, and we know the gravitational field strength. So we just substitute in the values and compute. So 2 pi times the square root of the length, 1.83, over 3.72, which is g, all square root. I'm so confident I'm not even going to check, but you definitely should. And that will give us 4.41 seconds when it's rounded. Right, so you should write your unrounded answer in case you need to use it in further calculations, but you know, we're rounding it. And that is an achieved question. Since it is a show that question, you do need to at least show this step where you put the values in, but I recommend also showing the first step by stating the equation. Alright, let's move on. Now they set the pendulum oscillating by releasing it, so they pulled it back 0.3 meters in the horizontal from its rest position, right? So this is where it would hang down naturally. And they let go and start a timer. The question is, determine the position of the pendulum. So we're looking for a position. So an SHM, well actually we use Y, don't we? Oh, but since it's the horizontal direction, let's use X. The position of the pendulum from its release point 2 seconds after it is released. You may draw a phasor diagram if you'd like, but I'm going to show you the way with the SHM equations. So, looking near the bottom of your formula sheet, you see 2 rows of equations. Actually, let me just pull it up. Alright, I just pulled it up. So this is your mechanical systems formula sheet. See the bottom 2 rows here? Y equals a sine omega t, and then the one below that, y equals a cos omega t. Yeah. So those are our SHM equations, which model the displacement, so y or x, the velocity, v, and the acceleration, a, at any point in time during its motion. And so you'll notice they all depend on a, which is the amplitude, right, the maximum displacement, as well as omega, which is the angular frequency. And what does omega depend on? Well, let's have a look in our formula sheet. Oh, I'm so blind today. Oh, here we go. Omega equals 2 pi times the frequency. Yep. Where frequency is 1 over the time period. So if you combine these two equations right here, you could write omega as 2 pi divided by the time period. Cool, so let's go back to our work. So I'm going to do that first because omega is an important parameter in an SHM equation, 2 pi over t, where t is the time period, and we already worked that out as 4.41 seconds. Cool. In fact, we should use the unrounded answer, which would be 4.4069, giving us 1.43 radians per second. So the angular frequency is 1.43 radians per second. If you stop there, that is an achieved point. And now, all we need to do is decide which equation we will use. So going back, we are looking for a position, right? So a displacement. So we are choosing either y equals a sine omega t or y equals a cos omega t. So those are our options. So let me just write them both down. Cool. And how these differ is the sine omega t is where the movement starts from equilibrium. So it starts from like x naught, the rest position, whereas a times cos omega t, it starts from x equals the amplitude, right? A maximum displacement. So in this context, we let go of the pendulum away from the rest position, so it's at a maximum amplitude. So we will choose this equation right here, y equals a cos omega t. So let me just do that on the right. We know omega is 1.43 radians per second. What else do we need? We need amplitude. So what is the maximum displacement? Well, we're told they pull it 0.3 meters back. Oh. A equals 0.3 meters. And so we can write, I'm going to write x here instead of y, but you know, that's just convention because it's in the horizontal direction. You can write y is totally fine. X equals the amplitude times cosine of the angular frequency times time. And we are told the time, aren't we? So t equals 2 seconds times 2. So x equals, get out our calculator. Now, being careful here, we have a trig function. Do we want degrees or radians? So, what am I in? I am in degrees. Let's just see what happens, see if it works, and then we'll explain why. So 0.3 times cosine of 1.43 times 2, close bracket, 0.299. 0.299. All right, and shall we try radians? Oh, radians. Exit out of that. 0.3 times cos of 1.43 times 2, close bracket, negative 0.288. Okay, so those are quite close, which doesn't help for the common sense check. So 0.299 would mean that it swung and it came back and it almost reached the 0.3 meters, right? It's 0.001 meters off. Okay, so let's have a think. So the time period was 4.41 seconds, and it's asking after 2 seconds, which tells me after 2 seconds would sort of be about here. Oh, right, if the other maximum was over here, there's half a period, 2.2 seconds would be at the opposite maximum, so negative 0.3, so it's not quite going to reach that, which means we are expecting about like negative 0.27 or so. Okay, so looking back at our working, we cannot use degrees to solve this type of question, because recall angular frequency is measured in radians. Right, so the correct answer, so let's just put in red, so in radians. In radians, our displacement is negative 0.288 meters. Cool. And are we done? Determine the position of the pendulum from its release point. Ooh, okay, so they're trying to trick us here. From its release point. So what's one final step we need to do? Well, if we started here, we went 0.3 meters, and we went a further 0.288 meters, the distance from that release point, so x release would be 0.3 plus 0.288, which is 0.588 meters. All right, let's go through this one more time. This was the excellence question. So it's asking us to determine a position after some time. We know it's simple harmonic motion. We have found the time period. We can easily calculate the angular frequency, 2 pi divided by t, which is used in the displacement time SHM equation. And we chose to use y equals a cos omega t because it's starting from a maximum, right? From its release point, which is at 0.3 meters, as opposed to starting from the rest position. So we picked our equation. We know A was 0.3 meters. We know omega because we worked it out, and we were given T. So plugging in those values, we found after 2 seconds, it would be at 0.288 meters to the left of the rest position. And so if you stop there, that would be a merit, and the final point would then be to add 0.3 meters because it asked the distance from release point, as opposed to distance from rest position. So just be careful on that last bit. And of course, we did it in radians. Whew. All right. It's downhill from here. That was the hardest question, or sub-question. Part C, the amplitude decreases from 0.3 meters to 0.2 meters. So after a while, of swinging, its amplitude started to decrease. Explain why the period remains unchanged. All right, 2 ways to explain this one. Let's start with the easy one, in my opinion, and that is all to do with the definition of its period. T equals 2 pi times the square root of L over G. Notice L and G are constant. So T is constant. Right, we don't need to say pi is constant, that's a given. So L and G, length and gravitational field strength are constant, so the time period is constant, which tells us T is independent of A, of amplitude. The time period does not change with amplitude. Cool. So we stated the equation, we explained that L and G are constant, which means the time period is constant, and we linked it back to the context of the question in saying that it does not depend on amplitude. Great. So that is, in my opinion, the easy way of answering this question with the formula. That would get you the full marks of merit. But let's look at the other way, which sort of explains simple harmonic motion a bit more. And so definition of simple harmonic motion: acceleration is proportional to the negative of displacement. So as displacement grows, the acceleration increases, and they're just acting in the opposite direction. So if displacement decreases, so as amplitude, which is max displacement, decreases, acceleration also decreases. And so if acceleration decreases, it means it will cover less distance in the same time. So smaller distance covered as a slower speed. Cool. And then answering the question, so period is constant. Cool. So again, this explains simple harmonic motion. Acceleration is proportional to displacement. As max displacement decreases, the acceleration would decrease, which means it's going to be swinging for a longer time. So it covers that smaller distance in a longer time, and that time is equal to t. So t remains constant. In reality, things like friction would have an effect on the time period, but here in SHM, we are ignoring that. Alright, question D. Calculate the total energy lost when the amplitude decreases. Begin by calculating the maximum velocity for the initial and final amplitude. Alright, so they've given us a prompt to get started, so let's do that. Let's have a look at our formula sheet. How can we find velocity, maximum velocity? So in the bottom sort of two rows are our simple harmonic motion equations. We can look at the velocity column here and recall if it was released from maximum, we're looking at the bottom row. So V equals negative A omega sine omega t. And so V max, well, let's just write out. So V equals negative A omega sine omega t. The sine function, in case you forgot, oscillates between +1 and -1. So if we want the speed to be a maximum, this sine omega t must be 1 or -1. Right, and we're left with a maximum velocity possible of negative A omega. or we could drop the negative because that's just giving us like a direction. And if we're looking for energy, we don't care about which way it's swinging. So the maximum velocity is equal to the amplitude times the angular frequency. And notice the amplitude does change, but the angular frequency remains constant. And we calculated that before, 2 pi divided by the time period. So let's write 4.3 meters. V max is equal to 0.3 times 1.43 radians per second, giving us 0.429 meters per second. And for the smaller amplitude, the maximum velocity is the amplitude times the angular frequency. And what's that? 0.286, according to the mark scheme, meters per second. All right. And now, how do we relate that to energy? So think of the pendulum, right? It starts with potential energy, it reaches a point, then it's got maximum kinetic energy, back to potential, back to maximum kinetic, and so forth, right, as it oscillates. And so we found the maximum speed, so we can relate that to the maximum kinetic energies. Half times the mass, were we given the mass? 2.3 kgs? Yep. Half times the mass times the speed squared. And that gives 0.212 joules for energy. And then for the 0.2 meters, half times the same mass, right? Mass hasn't changed, but the maximum speed has changed. 0.286 squared, giving 0.0941 joules again. And so notice the maximum kinetic energy has dropped, and that drop in kinetic energy corresponds to the energy lost, right, due to heat. So energy lost equals the maximum initial kinetic energy, take away the maximum final kinetic energy. 0.118 joules. And that is a merit question. If you just worked out the maximum speed and did some, like a silly mistake, like with a sign or a significant rounding error in the kinetic energies, you can still get achieved for that question. Alright, that's it for this one. See you next time.